Swayam Prabha. Digital India. Educated India.
Welcome back. In lecture 57, we will cover groundwater recharge, part 2. The different concepts that we will cover are on artificial recharge techniques, within which we will cover surface spreading techniques, subsurface techniques, groundwater conservation techniques, and then we will finally look into rooftop rainwater collection and recharge of groundwater. So, artificial recharge techniques could be there could be direct methods and indirect methods, and within direct methods the first group of techniques could be called under could be categorized under surface spreading techniques. So, as you can understand, in this case the water is spread over the surface. So, the techniques are like flooding, ditch and furrows, recharge basins, then runoff conservation structures and stream modification or augmentation, and within runoff conservation structures we can again have many techniques such as bench terracing, contour bunds, gully plugs, nala blunts, check dams, percolation ponds, and so on. Then subsurface techniques, that you can understand, that means we are directly putting the recharge water or this water for groundwater recharge into certain wells or which is below the surface, and these are injection wells, also known as recharge wells, gravity head recharge wells, recharge pits and shafts, and so on. And as you can see in this image, there are different forms of recharge techniques for increasingly deep permeable materials. Like this is a surface basin which is mostly about surface spreading, whereas there is an excavated basin, then there are trenches, then there are shafts or Vados zone wells, that means a little bit deeper wells, and then there is the aquifer well, that means the wells which take in the recharge water much below at a much lower level, where we can actually reach multiple aquifers. Then there are indirect methods. So, like these are the direct methods, and then there are indirect methods. That direct methods actually increase the water at a particular location, the groundwater in a particular location. Indirect methods actually doesn't put in water in that location, but actually draws water from other locations. That is how it is done. Like it is done through induced recharge from surface water sources by pumping. That means, if you keep on pumping an area, automatically you create that hydraulic gradient, and as you have learned earlier in case of deep tubewell construction, so if you keep on pumping, water will start flowing from the surrounding areas, right? And this induced recharge from surface water sources, that means if there are nearby surface water sources, and of course that water will come underground or travel via those soil pores into this particular aquifer, because we are pumping from this aquifer because of this difference in hydraulic gradient. And usually when we pump, these pathways open up, and these pathways, even after pumping, the pathways will remain open and water will start flowing in by its normal pace. So, pumping actually starts this process, and this is one. The other is by aquifer modification. That means we can by board blasting or hydrofracturing, sometimes we can connect multiple aquifers or connect some aquifers, and through that we can transfer water from one aquifer to another. So, that is we can also increase the yield in this particular way. So, these are indirect methods. So, we are not actually putting water in a particular area, but drawing water from surrounding areas. Then there could be combined techniques. Combined techniques, as you can understand, that where we can have a surface spreading technique as well as a subsurface technique. For example, if I have got this kind of a excavated basin, and if I put some trench or to it, it becomes a combined technique. And then subsurface, then there are groundwater conservation techniques. That means we try to retain the groundwater that is there, and we use certain kinds of structures for that. And this, like for example, subsurface dikes. Dikes are sort of dams. So we create some dams below ground, and these are known as bandharas. So this is some traditional structures. And then fracture sealing cementation techniques. So similar to bore blasting, we can also seal certain fractures so that water doesn't goes away, and this prevents subsurface flows. So these are the different kinds of techniques, and now we will look into some of these important ones, some of these important techniques one by one. So first we will look into surface spreading techniques, and as you understand that the contact area and residence time of the surface water over soil is actually increased to enhance infiltration and groundwater recharge. So normally when rainfall happens, the water falls on the ground, some amount of water percolates, but most of the water flows away as runoff. But if we want to increase the contact time of water with the soil, that means if we can create some depression where the water gets stored for some time, then it will get more time for percolating below ground. Otherwise, because of the slope of that particular land, the water will flow away and there is no chance of water percolating down. So surface spreading technique actually tries to increase the time the water keeps in touch with the soil, and that actually increases time of percolation, and that enhances filtration. So the aquifer, because we are doing surface spreading, the aquifer needs to be unconfined. So you remember what are confined aquifers and unconfined aquifers? So unconfined aquifers means there is no unpermeable surface over it. So that means directly water can percolate into this particular aquifer. So it is permeable, it should have high infiltration rate, that means the soil should have high permeability. It adequate storage and moderate hydraulic conductivity. It should have adequate storage, but it should have moderate hydraulic conductivity. That means water should be retained. It should not pass away faster from this particular aquifer. So usually we can use gentle slope with gullies and ridges inside this for improving this particular surface spreading or storing this particular water during surface spreading. So these are some of the techniques. We have got flooding technique, we have got ditch and furrows, then we have got stream channel modification. So these are the three basic techniques that are used when we do surface flooding. For example, when we do flooding, it is usually suitable for lands besides rivers or canals, and there is a lot of water over there. So over here you can see this is the stream channel, water is passing like that. We actually allow the water to go in this particular canal maybe, and from there we allow the water to flow as a sheet on that particular land, and we have another ditch that we have dug over here, which acts as a return canal. That means excess water which flows over the land comes to this ditch, and then it again flows back into the water body. So we are just making sure the land beside the river, we are able to percolate some amount of water on it, and that actually increases the groundwater of that particular area or that particular aquifer. The ditch and furrow system is more or less similar to this what you have just learned. Over here it is a more structured system where shallow, flat bottomed, closely spaced ditches or furrows are used to increase water contact area for recharge, and these are also sensitive to silting as well, because you are taking water from a river, it increases silt. So we create diversion structures over there, sort of dams. So these are the different supply ditches that we have to construct, and then at different portions we can have these smaller check dams, and using this we can actually control the flow of water into these ditches. So these are ditches that are being constructed into the area. So it is not flowing on the surface, but flowing via the ditches, and from there it is spreading on both directions, right, underground. So it is not through surface flooding, but by putting the water into the ditches in this particular recharge area, we are able to percolate the water in the ground. So even though these are ditches, the excess water from the ditches could eventually come to this particular collecting ditch and again return back to the river as well. So adequate slope to maintain flow and minimize deposition for this particular ditches. So if the slope is too less, then there will be a lot of deposits that we don't want, and usually the width of ditches is around 0.3 to 1.8 meters. So, these are very thin channels, not too much wide, and there are also collecting channels which convey excess water back into the river as well. So, this is how the designs are for ditch and furrows. There are different designs. There is a lateral ditch pattern. So, this is the lateral ditch pattern, this B is the dendrite ditch pattern, this one, and C is the contour ditch pattern. So, this more or less follows the contour profile of that particular area. So, we can create these ditches in different patterns, and accordingly these names have been given. Similarly, we can also modify the stream channels, and that means if we have a water body going like there, usually during other times of the year, maybe sometimes the water spread into the surrounding areas, and usually the profile of that stream would be something like this. With this is the main body where the water flows, then these are the surrounding area which are also low, but we do not see water in all the time. So, we can actually modify this particular surrounding area to bring it down, and then actually expand the surface of that particular stream, or help the water to spread in a larger area, and actually that will increase recharge. Then we have got recharge basins. So, these are very these are more engineered structures than the other that we have just discussed, and this is also one of the surface spreading techniques, and usually these are constructed parallel to intermediate streams and canals, and these are excavated or enclosed by dikes and levees. Levees means the raised land, and these levees are provided so that the water does not flows out of this particular recharge basin. So, it is a recharge basin. So, it is an engineered area where we raise the sides of that particular area or create levees, and in between the levees we can also construct dikes as well. So, that actually increases the contact time, reduce suspended material, and allows periodic maintenance by scraping of silt by bypassing this same. So, that means you see this is the water body, this is that stream that we are talking about. This is the point where we intake the water. That means we take the water from this point of the river, and the first thing is we take the water through a sediment retention basin. So, that means the sediment is actually captured over here. So, you have learnt about sediment basins. The deposition rate has to be the area has to be such that it is adequate for water to travel from this point to this point. The time taken for water, it should be such so that, or the area of this sediment basin should be such so that there is adequate time for the sediments to deposit, right. So, that is the first thing that we do, and then you see the water entering into this particular recharge basin, and then within the recharge basin usually we follow our diagonal movement pattern, like over here the water comes like to this side, and then these are this inter-basin control structures which allow water to travel from one basin to another, and then from here again diagonally it goes to this side, and then once it enters, then we can use this way, and eventually it goes out and back into the stream at this point, right. So, this is how we design a recharge basin. We give a gentle slope with diagonally placed entry and exit points which facilitates water circulation, and rate of inflow into the basin is little more than the infiltration capacity of the basin, or it could be multiple basins as well. So, as you can see that we have sediment retention basins, we have got levees which are protection walls around this particular basin, and then we have got this different multiple basins which are connected by this inter-basins control structures allowing movement of water. And what we can do is like there are two flow channels, we can use one flow and stop the other, and then we can clean those particular side, and then when this part is clean, then we can do the other ones. Cleaning means if there is lot of deposits of silt, we eventually after certain time periods we have to clean it. That means you have to scrape it and remove those particular silt. Then we have got runoff conservation structures, and these are some form of surface spreading as well. So, in addition to groundwater recharge, this helps in of course, this helps in groundwater recharge, but it also helps in soil conservation. That means it prevents erosion, it helps in afforestation, and also useful for agricultural productivity. Particularly for hilly areas, water is difficult to hold the water. So, that is where if you want to practice agriculture, we need to hold water, and that is where this runoff conservation structures comes in. So, the first method is bench terracing. So, as you can know in bench terracing that if I have a profile of a hill like that, we usually create benches, and we level the slopes up to 8% with adequate soil cover to facilitate irrigation and recharge. So, we create these flat spaces and we level up to 8% slopes could be leveled, and then we create these benches where we can actually or terraces where we actually can do our practice of agriculture, and we can store water over there as well. Contour bunding is we do not create benches, but at certain intervals we create trenches where the water gets trapped, and following the contour lines of that particular site, of course. And this in addition to contour this bunding, that means we raise the this is the bund part, and along with that we can also have contour trenches as well. So, usually these techniques are done in combination, but we can also do them separately. That means, if I have a profile like this and if I raise the soil at certain points, so some amount of water would be retained over here. So, that is contour bunding. And if I in addition to contour bund, we can create trench over here. So, more amount of water would be retained. So, that is where both contour bunding and trenching could happen together, and that is what is shown in this particular plan. So, this is the contour lines. We have created these bunds as well as trenches in front of it, so that we can retain water and use it for agriculture. So, in addition to all this, to reduce erosion, we have already learnt about check dams. So, gully plugs, nala bunds, check dams, these are all similar structures. These are constructed across gullies, nalas or streams to check the flow of surface water and to retain water for longer duration. So, if we have a channel, usually we have the structures in between, raised structures, and then at certain intervals, so that in between water is captured and retained for some amount of time. Then comes the most what to say the percolation tanks, but as you understand that this is where we store the water for some amount of time, and this percolation, all the other surface spreading, and we form some form of depressions in the ground where we store the water or increase the infiltration time, but mostly are designed for continuous flow of water. But in percolation tanks, we design the system so that the water is retained. So, these are surface water bodies created over highly permeable area to recharge the groundwater storage, and also helps in flood control in a particular catchment. So, excess water that is stored in a percolation, when the percolation tank's water level goes high and it feels like it would spill over the bunds that we have created or the raised structures around this particular tank that we have created, then of course, we need to have masonry spillways as well, through which the excess water will be diverted off to to the drainage channel maybe. So, this is what percolation tanks are all about, and the size of this particular tanks, as you can understand, this is of a larger scale. That means, we want to prevent flood. It is not only about recharge, we are preventing flood for a particular area. So, usually we consider the entire catchment that we are dealing with, and usually we require small tanks for catchments of 2.5 to 4 square kilometer areas, whereas for catchments of 5 to 8 square kilometers of areas we require large tanks. So, urban areas, semi-urban areas, we do not have catchments bigger than this, right. So, that means for 5 to 8 square kilometer we will need to have larger tanks compared to this small tanks for 2.5 to 4 square kilometer. So, we can take approximate yield values of areas, yield of rainfall for particular areas, and as 0.44 to 0.55 meter cubic meter of rainfall, million cubic meters of rainfall per square kilometer. So, that is the quantity of in million cubic meter of rainfall that happens per square kilometer that needs to be stored in a percolation tank. So, the percolation tank size of course is based on the total yield of water or rainfall that is falls on that particular area, but it also depends on or actually it is more important to consider the percolation capacity of that particular strata. So, it is not only the amount of rainfall that is there in that particular catchment, but at what rate the percolation happens in that particular area, that determines the size of that particular percolation tank. And as you understand, this is a tank, means it's a depression in the ground. As soon as rainfall starts, suppose it's a rainy season, the first rainfall happens, the water starts flowing, it comes to the tank, it starts percolating. So again the next rainfall happens, the next rainfall event happens, again the water comes and gets stored in the this particular percolation tank, and its infiltration is continuously happening. So it's not like the entire volume of rainfall from that particular area will come for that entire year maybe, or for that rainy season will come and has to be stored in that percolation tank, because percolation is immediate, right. So percolation capacity is more important compared to the total volume or the yield of that rainfall yield for that water yield from that particular catchment. So usually we go for smaller mid-sized tanks, and this is because smaller and mid-sized tanks, the evaporation rate is lower, and the size of these tanks are around 2.26 to 5.66 million cubic meter. So as you can say, if you 0.55 million cubic meter is per square kilometer, then you can understand that 2.26 will probably have 5 square kilometers of yield of rainfall. But again, I said that it's not for the total yield. The size, volume of the rainfall, volume of this particular percolation tank is based on both the percolation rate and the rainfall. So actually the rainfall may be even double of this, right. So that means or the area that is considered could be double of the yield actually. So 2.26 divided by 5.5, we get around 5 square kilometers, but actually the area may be 10 square kilometers of area could be covered by this sort of tank. Depth of water in the tank is around 3 to 4.5 meter and rarely 6 meters. And why this depth is given? So that it creates that recharge head, because the water in that particular tank, this is the recharge head, this is the depth of water. So this creates pressure for water to percolate. So that we create that pressure difference by providing a higher height of this particular water. And this is located downstream of runoff zones, and usually a slope of 3 to 5% is given to this kind of percolation tanks. So to summarize, percolation tanks are designed considering a realistic percentage of the yield of the catchment and temporal distribution of monsoon rainfall. So it's not the entire thing, a realistic percentage of the yield of the catchment is considered, and water stored in a percolation tank starts percolating immediately, and the terminal storage in the tank is not the cumulative storage from different spells of rain. So this has to be kept in mind, that we just cannot determine the total rainfall and determine the size of this tank, because percolation is also immediately happening. So to design a percolation tank, again I am not going too much into the engineering design, but you can see that we need to understand the storage capacity of the tank, that will determine the area that is required for the tank. There is a waste weir in the tank, then there is a drainage, we need to consider the drainage from the tank. There is something called a bund, and then there is cut-off trench. In this particular image you can see the bund over here, that prevents the water to flow out. So that also gives the height to this particular percolation tank, because this depression probably is available on the ground. We don't do further excavation. We instead create bunds around to create that extra height where water could be stored. Now, what is a cut-off trench? Usually we give a cut-off trench like this. We will excavate in the ground, we create, and then we fill this with clay soil, and because clay soil is not permeable, and then the water is not able to go out of this particular percolation tank from the surrounding, only it will go down below. So that is how a percolation tank is designed. And percolation tank storage capacity is basically the volume of water stored in the tank up to the full tank level. So this is the full tank level, FTL. So from that we determine the storage capacity, and usually it's a large area, it's not a small area. So the total capacity of the tank is basically the sum of capacities between successive contours. So we have contour lines. So this actually gives us an idea about the profile of that particular tank, and this the area between the successive contours and their depth, that actually could be multiplied, and then we can determine the total volume of water that is being stored. But in absence of the contour details or this kind of data, we can just assume that area is equal to the surface area into 1/3 of the depth, that is FTL to the deep bed, this one, So, this distance we can take and multiply with 1/3 of that, and we multiply it with the surface area, and then we can also get the total volume of water stored in this percolation tank. So, to design percolation tank, we already talked about this percolation capacity, but roughly we use to determine the total yield of that particular catchment, that is how much rainfall falls in that particular catchment, we can use area of the catchment multiplied by Strange's coefficient, which there are different forms in which Strange's coefficient is given, but in this particular table you can see we have got daily rainfall, runoff percentage and eventual yield. So, that means daily rainfall is 5, 10, 25, 40, 60, 80, 100 mm, and runoff percentage is given as 1, 3, 7, 14, 22, 30, which will vary from different types of catchment. And then these are the yields in each of this case that we can directly pick up from the table based on the runoff percentage, and then from that we can estimate the total yield of that particular catchment. So, this is Strange tables, and this is again given for dry. Similarly, for damp area and wet area, these values would vary. So, that means for dry area the runoff is 30, then whereas for damp area the runoff is around 50, right. So, that is whereas for wet area it is 70. So, why? Because if the area is already the antecedent moisture conditions, if you remember from your SCS CNN lecture, that if already there is lot of moisture in the ground, then definitely the runoff increases. So, that is what is happening over here. So, in addition, we can deduct or add or deduct 25% of the yield for good or bad catchments. Now, what is a good catchment? Good catchment are hills or plains with little cultivation and moderately absorbent soil, and bad catchment is flat and cultivated sandy soils. So, in that case we can deduct 25% of yield, whereas for good catchment we can add 25% of yield in addition to this particular values. And yield's Strange coefficient is also available for total monsoon rainfall in Indian context, right. So, or it could be for each rainfall event we can also determine these values. Then we come to subsurface techniques, and usually these techniques are utilized or this kind of structures are utilized for recharging deep aquifers, and with particularly with impermeable layers on top of that means there are multiple layers of the aquifer, and with some aquifers with having impermeable layer at the top, that means water cannot percolate directly from that above, that means we cannot use surface spreading techniques. So, that is where subsurface techniques are required. And the first type of subsurface technique or structure is an injection well or a recharge well, and these are similar to bore wells or tube wells in construction, but these are used not for extracting water, but for recharging water in case of overexploited aquifers, and this could be done both under gravity or under pressure. That means the recharge could be done with we can put the water under pressure, or it could be just via gravity. So, as you can see the structure of a recharge well, and these are multiple aquifers. This is aquifer 1, this is aquifer 2, and you can see the aquiclude in between. This is the hard stratum, right. And so, that means there is no transfer of water between the aquifers because of this presence of aquiclude. So, we are putting this conductor pipe and inside, through which we are actually recharging the water, and this is the casing pipe, this dotted one, and through this casing pipe we can the water goes out into the aquifer, and at the side of this we have got this gravel put in, so that the water can pass through that and then only go into the aquifer. So, whatever we have learned for dip tube, it is just the reverse of that. And in addition, there are trimming pipes. This is through which concrete or these gravels are actually poured through, and these pipes are actually utilized for pouring in this particular material, and that actually is also done for this 2 levels of aquifer. And in between this particular aquifer, we also have got seals, so that water cannot travel in between, and so more or less we can actually put in water via pressure, via pump, or we can put in via gravity. So, injection also prevents, so we know already that this kind of injection wells are particularly used where seawater is a issue, or coastal this seepage of saline water, ingress of saline water is an issue. And because we can we can put water in aquifers which are much below, that means at lower level aquifers, and that means we can also prevent land subsidence. That means because of over exploitation, sometimes this aquifers would be empty, and then it for the gaps between the different layers of soil, they collapse, and then there is subsidence. So actually by putting back water, we can prevent this kind of subsidence, and we can recharge single or multiple aquifers and using this kind of recharge structures. So usually we put a cement seal on the top to prevent leakage due to injection pressure. If we are injecting via pressure, that we put a cement seal at the top, and maybe at over here and over here, and over this actually is also that grout that we put in. This is the entire area which is sealed, so that the water doesn't comes up. And similar then wells with slotted pipes against the recharge zone for multiple aquifers, same as a deep tube well. That means we have slots open up at different levels through which we want water to actually recharge in each aquifer. And clogging decreases injection rate to 40 to 60% over time. So we also have to adjust the pumping rates and the pressure in that particular recharge structure, because eventually the pores would be clogged. And the pressure head of hydraulic injection is usually 1.2 times the depth of the total confined aquifer. So it is not too high, it is just 1.2 times the depth of the top of the confined aquifer. And if we put in too much pressure, it may actually break the this casing, and it will break this surrounding gravel structure, and it may have also ruptured the aquifer as well. And the size of conductor and casing pipe is determined based on how much amount of recharge we are able to do for this particular aquifers. So maybe you can see that 100 mm, 150 mm, 200 mm, this kind of diameter pipes can be used, and 100 mm can handle around 50 cubic meter per hour of recharge, 150 can do 150 cubic meter, 200 can do 250 cubic meter per hour, and so on. Then gravity head recharge wells, and as you can understand, we use gravity over here to make sure that the recharge is done, and we use this existing dug wells or tube or bore wells which are already there, and which are of no use because already the water has dried up in those aquifers. And this is where we can actually put in water via this particular structures to raise the water table, and in this case we do not need to put in any extra cost or investment for developing any kind of recharge structure. So during rainy season, when extra water is available, we can put the water back into this particular wells, and that will actually increase the level of the water table in that particular areas. So usually wells of higher yields are suitable, because if we can extract more water, similarly we can put in more water. And the recharge head or gravity head, so this could be achieved because it is a gravity well. That means we may not use pump, but we can actually raise our reservoir and use that raised reservoir to put water into this particular well, and that actually creates that gravity head. And elevation difference between surface water level in the feeder reservoir and the water table actually gives this particular gravity head, which we will try to again follow as 1.2 times the depth of that particular recharge well. And source water should be adequately filtered and disinfected, and for any kind of recharge we need to actually have only filtered and properly disinfected water only put back into this in the groundwater. So in addition to this gravity well, we can have recharge pits and shafts. So recharge pits are basically basins where these are artificial recharge structures used for recharging shallow aquifers separated from ground by low permeability layers, and recharge via infiltration through the vadose zone, unlike injection wells. So these are just depressions that we dig in the ground, and we allow water to seep through the vadose zone into the nearby aquifers. And Recharge pits could be deep excavated pits similar to recharge wells, but are deeper and have restricted bottom area, and these are maybe abandoned quarries and all, like you can see over here. So, these are abandoned quarries which could be filled up, through which water can recharge. So, then comes recharge shafts. So, these are smaller in cross section than the recharge pits, and these are around 1 to 2 meter diameter, and we use unlined shafts which can be backfilled. And we use an inverse filter system where the boulders goes at the bottom, and this could be followed by gravel and sand. Then we will look at some other groundwater conservation techniques, like over here. This kind of techniques are designed so that the groundwater is retained for longer periods in a particular basin or a watershed, and some of this like groundwater dams or subsurface dikes or underground bandharas. So, these are traditional structures, and we can also do fracture sealing cementation techniques as well. So, as you can see in this particular image, this is the catchment area, this is a stream, and there is groundwater. So, we can understand that because of the slope of this land, the water flows in this direction. So, this is where we are creating a clay or a concrete wall which prevents water to go down, and that actually retains groundwater in this particular zone. So, that actually some amount we can say that groundwater is being conserved in this particular areas. So, this subsurface dike or groundwater dam acts as a barrier and arrests or retards the groundwater flow, and that actually helps in increasing the groundwater storage in this particular area. And this could be constructed particularly across streams or valleys of 150 to 200 meter wide, and to create storage reservoir with suitable recharge conditions and low seepage losses. So, this you can see, this is this kind of this dams, like over here you can see the design. So, this is where this is based, the dam has to be constructed till there is impermeable rock, so that water does not leak through below. And then you can see this is the design where it could be 5 meter deep with a bottom width of 2 meter, or it could be even 15 to 20 meter deep with a bottom width of 5 meter. And the side slopes are given as 2:1, and this is how we can actually prevent groundwater to pass from one area to another. And usually these are constructed across streams, and the length of this particular dikes around 150 to 200 meter wide. So, now we will talk about recharge in urban areas. So, what we have been discussing is some of those could be constructed in urban areas, but many of those are not suitable for urban areas, and it is for a much larger scale. But when we talk about rainwater harvesting or rooftop rainwater collection and recharge of groundwater, then we are actually looking into urban areas or urban catchments. So, usually the rainwater that falls on the roof, we have already discussed that we can actually store that water, and we can use that water for either domestic use, or we can use the water to actually percolate and then recharge the groundwater. So, you can see in this particular image we have this roof catchment, the water comes down to this gutter, and this is being captured over here, then it comes down. The first flush could be taken down, then once the first rainfall event happens, then we can close it, and the water is directly taken to a storage tank, from where we can use the water, or the water can go to a recharge pit from where the water could be percolating inside the ground. So, I will show you designs of recharge pit, but before we go into that, we can also actually do some amount of treatment of this particular water, like in this particular design. If I elaborate on this is rainwater is coming in, then first shower goes to the drain directly. So, we have this valve over here, this valve is closed, then we close this particular valve and open this one, and all showers after that can go directly like that. So, if excess water is coming in, some amount of water could be drained, but the most of the water has to be taken through this particular filter, and then we can take it either to recharge or to storage. Now, what is this filter? This filter is, that means the water that is collected on our roof, some amount of basic treatment is done. How it is done? So, we create this chamber which has got sand and we have got gravel. So, we allow the water to pass through both sand and gravel. So, most of the solids are trapped over here, and we get clean water which could be stored. So, over here we are using this structure is maybe a 200 millimeter dia PVC pipe, and we are using 1.5 to 2 mm dia sand, and over here 3 to 5 mm dia gravel. And using this we can actually clean the rainwater and then actually use it for storage or recharge. Now, why it is important that we store this rainwater? Just let us do a very basic calculation. Let us assume that the annual rainfall is 1000 millimeter, right, for a particular area. It is a high value, but still we can just assume that, and then let the roof area be 100 square meter. So, it is not too much, 100 square meter. Then the total rainwater that could be collected, we can just need to multiply this with this, that comes to around 1 lakh liters annually. Now, if I consider a 100 LPCD liters per capita per day consumption and the household size of about 4 people, then you can just multiply and see that the water is adequate for around 1 lakh divided by 100 into 400 LPCD divided by 400, that comes to around 250 days. So, first flush, even though we get rid of the first flush, this would be adequate for around 250 days of a year. So, you can see the huge amount of water that we can capture just from rain. So, if we can capture this water and we can reuse this water, not only we can store the water underground and it will be useful for recharge, but if we can directly use it for certain purposes, that would be adequate for many purposes that is in the for which we use water in that particular building. So, that is why the rainwater collection is very, very important. So, in addition to use of the water, we can of course recharge the groundwater using this particular system, where we use percolation pits, abandoned tube wells and all to actually do the recharge. And this and as you know that if we do that locally, then it will reduce the peak runoff, and thus flooding in stormwater drains would also reduce. And we can also add a filter unit, as we have discussed. So, this table gives you a rough estimate. It is pretty easy to estimate the quantity of rainfall and how much water is being collected, but this table which is available from the manual of artificial recharge of groundwater, you can see that for different sizes of roof area and for different amount of rainfall in millimeter, we can determine what is the total quantum of harvested rainwater from roof that we can collect. And using this table, you can easily determine what amount of water could be retained at the building level and then used for recharge or used for some consumption and so on, and that will also reduce the amount of storm water that comes to your municipal sewer network or to the municipal open drains. So, in case of rooftop rainwater collection, the roofs may be either flat or sloping. Accordingly, we have to decide. There we can use gutters, which actually are folded galvanized iron sheet or semicircular PVC gutters, and these are actually oversized to 10 to 15% to collect this rainfall. And pipes are used to carry water from the roof to the harvesting system, as we have seen in the previous figures. And the storage tank depends on the tank size is as per the use of water. That means, if I want to use 20% of this water, I will create a tank of 20% capacity. And these are placed above or below ground based on available space, and we can use reinforced cement concrete, polyethylene metal tanks, similar to any kind of standard reservoir that we use in our houses. And finally, we have to treat the water as using the system that we showed, or it could be through some other structures when we go for recharge. So, when we take this water for recharge, we do need to treat it to certain extent. So, we can use sand filters, and this sand filters could be also used to treat the first flush runoff before we use it for recharge. And usually it is just a bed of sand. So, this is a concrete structure, and we have this bed of sand over there, and with the topmost part we have a gravel layer, and below again there is gravel layer, and we put this under drainage pipes in which the water comes in, and that then it would be drained. So, this pipes could be taken for storage, this water could be taken for storage or could be taken for recharge, and these PVC pipes are wrapped in geotextile fabric to prevent entry of sand or this gravel inside those pipelines or clogging of the pipelines. So, these are usually used in runoff is filtered through this sand bed and used in urban areas for groundwater protection. So, we can also go for peat sand filter, the top layer of peat or grass cover before being strained through sand layer. So, instead of just using sand, we can have a top layer of peat or grass cover. Peat, it's vegetation and all mixed together. So, it's not decomposed vegetation, but it's vegetation which has been collected from the surroundings, and we make it into a mixture, and then it could be put in at the top of the sand layer, and then this is peat layer, purely peat, then there is grass cover, and this is usually a loose material which is based on this vegetation. And then we have 50:60 peat is to sand layer, and then finally we have got fine or medium sand layer, and then the washed gravel below that. So, this is the system of peat sand filter, which is similar to sand filter, but a little bit different design. So, the purpose of this kind of filters is basically to clean the water before it is being recharged, and this requires limited space. It does not require too much space, and it is not affected by evaporation rates, and could be used in areas with low infiltration and thin soil cover, and it can remove lot of sediment, and trace metals and all could be removed. Failure, these are pretty robust, they work pretty well, they do not fail too much, but they require frequent maintenance. You have to clean the sand to remove all those dirt that is captured into that, sediment that gets captured into that, and particularly the top layer has to be cleaned frequently. Similarly, we have got percolation pits. When we allow groundwater to percolate into the ground, then directly we can use percolation pits, into which we can also have these filter layers. Like in this particular image, you can see that we have put in boulders below, then above that is gravel, then there is coarse sand of 40 to 60 centimeter, gravel of 70 to 70 centimeter, and boulder of 80 to 120 centimeter. So, the water comes using this via this pipe, falls on this particular filter layer, and then gradually goes down and then percolates into the ground. So, roof area around for 100 square meter, we can have pit sizes of 1 to 2 meter wide and 2 to 3 meter deep, and these are filled with boulder, gravel, sand for filtration, and we need to remove the silt using sand filter before percolation. So, that is also possible. Then we have got percolation trenches. So, in case we exceed that roof size by 100 square meter roof size, that means we have got roof sizes of 200, 300 square meters. So, we require larger areas for percolation, right. So, in that case, instead of a pit, we make into a percolation trench. So, everything else remains same, but it is a trench. That means it's wider. That is usually the trench section is 0.5 to 1 meter wide. It's 1 to 1.5 meter deep, and the length depends on the roof area and the soil characteristics. So, the length of the trench should be as per requirement, and these are filled with boulders, gravel and sand similar to earlier, and we need to clean the filter media at certain periodic intervals. Similarly, we can use recharge wells. Dry unused dug wells can be used for roof area around 100 square meter. Water is brought down through 100 millimeter pipe to the bottom of the well, and then from there it automatically gets recharged. And storage of runoff in a percolation tank, that is also possible. But as you understand, if we put it in an open tank, then some amount of water is lost by evaporation. So, to conclude, the choice of recharge technique or structure depends on the recharge volume, scale of application, and availability of space and economic viability. Then percolation tanks are designed considering a percentage of the yield of the catchment and percolation capacity of the strata. And finally, rainwater harvesting is the most feasible and easy recharge option, which can be adopted at different scales. So, these are some of the references you can use. Thank you.